Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Module 13, Benchmarking. You are now watching Lesson 13.3, CPU-bound benchmarking.
Now that we know how to do some basic benchmarking, I want to do a little bit more maybe practical benchmarking and sum up a lot of the things that we've talked about or focus on a CPU-bound algorithm. We'll run it sequentially and we'll look at a concurrent version and we'll get an understanding of how parallelism is required with CPU-bound workloads if you want to get some better performance. All right, so let's take a look at the code. And what this code does is it generates a list of a million numbers. And we have two versions of a add algorithm. So we're going to generate a list of a million numbers. And then we're going to add all those numbers up sequentially, like you see here between lines 37 and 41. So we've got like 5 lines of code to write add. Really, really simple, right? We just range over each number, add it to the current total, and then return it. Okay. Add concurrent, however, is a little bit more complex. Here we're going to pass in the number of coroutines that we want to use and that same list of a million numbers. Now, there's lots of ways you can write this, but knowing that channels are slow and trying to find a way to not necessarily use channels, because again, about complexity, what I decided to do with this version of the algorithm is identify this stride value based on the number of coroutines. In other words, take this list of a million integers and break it up, in my case, into 8 pretty evenly cut lists, and then to have 8 coroutines, each ranging over their own slice, right, or portion of the list. And then once they're done adding their portion of the list up, we'll just add it back atomically to that global variable. So a lot of this code that you're seeing here, what do we have, about 20 maybe lines of code? A lot of it has to do with trying to figure out what that split is and then just making sure that everything is being orchestrated properly from beginning to end. Now, this is a CPU-bound workload, so what should our expectations be? Well, if it's CPU-bound and it's concurrent, and it's definitely concurrent work, we can definitely execute the adding of this list out of order. Then what we should see is that if we're going to only leverage one of the 8 hardware threads on my machine, then the sequential version should run faster than the concurrent version, right? That the context switches should be slowing us down. But then when we run this in parallel, we should see a definitely improved performance because we can process, in this part, 8 parts of that list in parallel. So this is what we should expect to see. So let's go ahead and look at our test now. Now, in order to really make sure that we get some accurate numbers here, I'm having the benchmark run each test twice. So sequential, then concurrent, sequential again, and then concurrent. I found that with these tests, if I did that, I felt like the results were more accurate. Remember, we talked about validating your results. So there's the benchmark sequential and concurrent. We're going to use, in my case, 8 coroutines always, and then again, and concurrent. All right, so let's see what we get here. We're in that folder there. And the first thing what we're going to do when we run this test is I want to turn the garbage collector off. So GOGC equals off, because what I don't want is the garbage collector coming in and skewing the results of this test, because we already know that the garbage collector will cause latency. So we're going to do go test. We're going to say run anything that might have a test function in it. Run all the benchmarks. I don't particularly care about memory here, but what I do care about is CPU. What we're going to do right now is tell the benchmark that it's only going to have one hardware thread, or 1P, 1M, single-threaded Go program to work with. Probably good as well to change the bench time to 3 seconds. So what we're going to do is run this CPU-bound workload. We only have one hardware thread to work with. We're a single-threaded Go program. So sequential is going to be able to leverage that thread. The concurrent version is going to try to use 8 coroutines against one thread. we should see problems with context switches in terms of performance. So let's see what we get. So this is our sequential version of add for those million numbers. We could see that it comes in at 7 milliseconds. And then if you see the concurrent version came in at 7.5. So almost really dead even, but the concurrent version is still a little bit slower. Remember, those 200 nanosecond context switches in this case are starting to add up. So really the sequential version is going to be faster, if not comparable, because we've got that those context switches coming in. And we can see on the other run that actually concurrent came in a little bit faster, which is interesting. But at the end of the day, running this concurrently is not giving us any better performance at all. We'd be better off not trying to leverage all of the CPU capacity on this machine. But let's run this benchmark again. And this time, let's use all 8 of those hardware threads that I know that I have on this machine, all 8. And let's see what we get now. So here's our sequential version. I'd expect it to come in just about the same, and it did, because even though we've got 8 threads available to us now, we're only using 1. But look how much faster the concurrent version is. You can see here that it's not nearly twice as fast, but significantly better when we give those Go routines their own thread to run in parallel as opposed to sharing the one thread. So this kind of validates what we talked about with understanding your workload. When you have a CPU-bound workload, if you're going to leverage concurrency, then you must also leverage parallelism. And using more threads or more Go routines than you have, in this case threads or hardware threads, isn't going to make you run any faster. You're just using more of that CPU capacity, but you're not really getting the throughput.